Hey everyone, just wanted to quickly recap. So first, we have these three equations from the previous video. Frequency equals waves over seconds, period equals seconds over waves. These will not be given to you. These are just the definitions of what a frequency and what the period is. This equation, on the other hand, will be given to you. The idea that period is 1 over the frequency. This is definitely an important thing so that you know that once you have one of these terms, just take the inverse of it and you get the other. So what we're going to talk about today real quick is about speed of the wave. Now the main equation that we use for speed of the wave is v equals f lambda. V stands for the speed of the wave. It's measured in meters per second. So that's pretty much how quickly the wave goes from one point to another point. Uh, we could also find this using distance divided by time if we know how much distance the wave covers in a certain amount of time. So just don't forget, v bar equals d over t does not go away. It can still be used in conjunction with this. So maybe part A would have you use that equation to find the velocity, and then you would use this to find something else. So this and v bar equals d over t are both viable equations. Frequency is measured in hertz. So if you have a number in hertz, you could plug that in. And then this symbol is called a lambda. Uh, it's spelt like this. It's another Greek symbol, lambda. And it stands for the wavelength. It is the length of one full wave in meters. So one full wave looks like this. That is one full wave, one sine curve. Or, though you probably wouldn't see it like this, one cosine curve is also one wave. So this is one wave. This would be two waves. This would be 2.5 waves, and so on and so on. So you need to have a crest and a trough in order for you to have a full wave. So this has two crests and two troughs, so it's two waves. This has three crests and two troughs, so it's only 2.5 waves. So here's a practice question. You're going to figure out what the frequency and what the speed are. Okay, so the way we're going to do this, the first one, they tell us that one crest passes every 4 times 10 to the negative 1 seconds. That is telling me the period. So I know the period is 4 times 10 to the negative 1 seconds. And as I said before, once I know one term, I immediately know that the other term is 1 over this. So if I plug into the calculator 1 over 4 times 10 to the negative 1, I get that the frequency is 2.5 hertz. All right. Now for the next one, they want the speed of the wave. Now I have to use this term. So they say the distance for the between successive crests is this, 1 times 10 to the negative 2 meters. That is one wave because this is a crest, this is the next crest. That's basically a cosine curve. So that gives us our wavelength. So our wavelength is 1 times 10 to the negative 2 meters. So using the equation that I have, I take the frequency, multiply by the wavelength, take the 2.5 hertz, times it by 1 times 10 to the negative 2, and I end up getting 0.025 meters per second. Now, if you wanted to, you could have found the velocity without using the frequency, because what we could do is, looking at this unit, meters per second, this number's in meters, this number's in seconds, you find that if you actually do instead v equals lambda over period, this would also get you the 0.025 meters per second, because as I said before, period is just a very fancy time. It's time for one wave. Well, it turns out lambda is also a fancy distance. It's a distance of one wave. So it kind of works itself out. All right. Here's the next question. All right. So for part A, they want to know how many waves there are. So looking at this, there's one crest, one trough. That's one wave. Two crests, two troughs. That's two waves. And then a third crest, but no more troughs. So that is 3.5 waves. So A would be 3.5 waves. Now, for part B, it wants to know what the wavelength is. Now, I didn't mention a specific equation for this, but if we go back to these two equations, we can actually do something similar. As I said, these equations come from the definition, and I just called wavelength as length of a wave. So what we can do is I can say that lambda is the length divided by the number of waves. So I can use this to figure out what the wavelength is. Going back to the problem, they told me that the full length is 5 meters, and I already figured out that it was 2.5 waves. So within 5 meters, the length is 2.5 waves. So that tells me that it is 2 meters. Now, one thing that I want to remind you, I know I said in the last video, but if you forget which one has to go on top, I always recommend looking at what unit you are supposed to end with, and that should be in the numerator. So meters, that's what lambda is measured in, so the meters goes up top. With the period is measured in seconds, so seconds goes up top. Frequency is measured in hertz, but none of these are hertz, so we'll just throw seconds on the bottom. So that's one way of doing that. We can also just quickly double check, and that this makes sense. 2 meters, 4 meters, and then this is half a wave, so that would be 1 extra meter, which gives us the 5 meters. All right. So some quick things that I want to mention about waves. With sound, the thing that is usually referring to loudness of sound is the amplitude. So things like frequency, period, wavelength, those are not affecting the loudness. So if you ever see a question that says, hey, which of these waves is the loudest, you're looking for the one with the greatest amplitude. For sound, frequency is affecting the pitch. So the difference between a high pitch and a low pitch is the frequency. That is also determined by period as well. Frequency and period, again, are connected. Higher the frequency, higher the pitch. Now, light's a little bit different. Amplitude is affecting the brightness. So if you've ever seen something like a dimmer switch, when you increase the brightness, you're increasing the amplitude of the light. And then frequency is actually affecting both the color and the energy of the light. So you saw it before, the electromagnetic spectrum, gamma rays all the way to X-rays and microwaves. Those are different frequencies of light. So different frequencies gives us different colors and therefore different energies. The higher the frequency, the more energy it has. Velocity is also dependent on the material that it's moving through. So the only thing that you really need to know about this is kind of like what scenarios would result in faster waves. Sound waves move faster in hotter and denser materials. So for example, in air, sound travels at 343 meters per second, but in water, sound travels at 1,400 meters per second. So sound travels about 4 times faster in water than it does in air because water is denser than air. Slinkies and string waves, so like if you take a string and you whip it and you're making a wave on that, it moves faster when the string is lighter and tighter. So the tighter you hold it, the faster it moves through. Water waves tend to move faster in shallow waters, and light waves tend to move faster in less dense materials. So, yeah, with the light waves, we'll talk about that a little bit more later. And that's it. I'm going to end it here. There'll be one more video with waves, and then I'm going to give you a little POCL. All right, if you have any questions, send me a message on Remind, and see y'all later.